Hello and welcome to my video on 8-bit bitmaps on the Nintendo DS. In this video I'm going to go over how you can set them up and then what you need to know to use them effectively. So let's get into it. So if you've seen some of the other videos, you'll see me go over the different screen modes for both the top and the bottom screen, known as the main engine for the top and the sub engine for the bottom. The top screen has more graphics modes than the bottom screen and has the ability for a 3D layer as well, which I won't go over in this video. But anyway, as we're working with 8-bit bitmaps here, the modes we're interested in are the ones which have either R, E or L for them, as they are all bitmap screens. So you can see here in mode 1 we can only have one bitmap screen, which has to be background free. So this is something to be aware of as well, is which backgrounds can only use the bitmap screens. So the good bit about it is you can obviously mix and match these, so you can have two bitmaps at any one time potentially, and then due to the ability to change the order of the layering, you can have one at the bottom. Maybe you want another text layer above that one, maybe another bitmap, and maybe a text layer above that one again. So the DS is quite flexible when it comes to this. The only limits that you're going to have will be video RAM, and as we'll come to shortly, the bitmap screens themselves, they can be configured in a number of different sizes, again depending on what mode you kind of have them in. For example, in mode 6 here, the large bitmap can have a size of 1024 by 1024. However, that will eat up pretty much majority of your video RAM if you have that. And notice that there's no other layers, so all you'll be working with is the very large bitmap. Although that's not really a problem, as I'll show in the demo. Basically, you can get around not having any of the other layers really when you have a bitmap screen, due to the ability to draw anywhere on the surface of it. You don't really need text layers for tiles. You can do it all yourself. It just makes life a bit easier sometimes if you have these tile layers, though, as it's obviously a tile layer takes a lot less memory than the bitmap screens, and everything's arranged slightly and takes less memory. So some of the things you can do with a bitmap, obviously R is for rotational. You can rotate them around. I won't be doing any of that here. And then the extended modes, you can increase the number of color palettes, but again I won't be going over that. I'm sure there's I think there's an example of using extended color palettes and also rotation and all that other sort of the other effects you can do with the bitmap screens in the examples for DevKit Pro. So most of the screen sizes here are power of 2, in that they are divisible by 2, and usually they're also divisible by 8 and 4 as well. So note here with the sizes, they kind of quadruple to some degree. Like, so we've got, if you've got 128 by 128 bitmap, that takes 16K of video RAM. Oh yeah, one thing to note as well is each pixel is 1 byte on 8-bit bitmap screens. This makes it really simple to plot pixels on and to manipulate the pixels on there as well, which is obviously of benefit to us. And then when you jump to 256 by 256, which is the normal size you would use if you want the bitmap to cover the full screen. And then there's also these larger sizes that you can have as well. But again, notice the size increases, potentially make it a lot more difficult to work with, especially when if I go over here to the video RAM banks, you'll see that one 512 by 512 pixel bitmap uses one video bank, and if you wanted 1024 by 1024, then you're going to be using all 4 of these banks together. So sub isn't going to be getting a screen. It also means the sizes of screens for the sub screen are limited as well, due to the ability to only use these banks in green to work with the sub screen. So another thing to note as well is when you use a 256 by 256 bitmap, obviously there's a chunk at the bottom of it that will not be shown because the screen's only 256 by 192. That hidden part of the bitmap is actually 16K in size, so depending how you arrange them, you could potentially put in a tile map there, or a tile set, or even a couple of tile maps, as long as you don't go into that area of the bitmap with your drawing. So when it comes to configuring these, there's a potential of 32 different locations you can use. So when you set them up, each location is in a 16K step. So this means that you can potentially go really far down in the video RAM, which is obviously needed if you're going to stack loads of these banks together. Then you need the ability to go further in video RAM than the tile modes would allow you to do. So you can assign multiple banks to the top screen. Excuse me. So if you are working with tiles and bitmaps, be aware that the tiles can't go that far down in video RAM, whereas the bitmap locations can. So if you're going to have a load of different layers active, it's probably better to have the tile layers at the top of video RAM and then have the bitmap screens further down. So when you set everything up, you kind of have to try and think where you're actually going to put these things. Sometimes some trial and error is obviously needed as well. So this bit here, basically we're just going about where the graphics RAM actually is mapped to. So for the main screen, that's 6000, and then for the sub screen, that's 620,000. These are all in hex. And then, as I just said here, there's only certain banks that the sub screen can have. So you kind of you have to plan out beforehand what you intend to actually use, which is fine. It gives you a lot of options, which is good. So working with tiles is obviously faster than working with bitmaps, but the DS is actually quite quick and seems to nicely cater for them. So one thing I mentioned in the previous video, which was on 256 color tiles, was that I was going to do sprites in here. I've decided not to do sprites in this video, 256 colors, so that I can purely concentrate on pix maps, as we will be creating virtual sprites from smaller sort of images, as you can kind of you can get away without actually using sprites when it comes to bitmaps. You just handle everything in software rather than hardware. What that kind of means is you're free to use any sort of size that you want, rather than them having to be multiples of 8. So you could do everything just using bitmaps. And then when it comes to the color palettes, so obviously we have 256 colors for the top screen, 256 colors for the bottom screen, 500,000 in hex in the main engine, and that one there in the bottom one. So the alphabet in each color can be useful here, so that some colors will not display over the others, which can be useful for when you're layering pix maps, or sorry, bitmaps, which I will be doing in the demo. So these are the bits associated with the color parts. For the color palettes here, we have 5 bits red, green and blue, and then 1 bit for alpha. So one thing to note is when reading or writing directly to video RAM, where you know the screen's pixels are located, you can't write in bytes. You can only write to video RAM using unsigned shorts or 32-bit numbers. There's no sort of ability for you to do 8-bit reads or writes. I'll show you a way to get around this in the actual demo. So this is basically how you can think of like a bitmap being arranged. 0, 0 is always the top left, and then depending on the size of the bitmap, so you can think of it as like a pixel map, as I've referred to it there, but the official names are bitmaps. So this would, the top left would be 0, the top right would be 255 by 0, and then the bottom right would obviously be, in the case of this bitmap here, would be 65535, or 255 by 255. But then, as I said before, the screen on the DS is only 256 by 192, so you kind of wasting the bottom part of the image. So I think that's most of the stuff here covered. So what I'll show you a few things now is some of the graphics used in here. So just like 256 color tiles, just set this off a minute. So just like in the tiles mode here, when you're drawing all of these, you'll want to make note, well, you want to first figure out how many colors each of the images you're going to be using has. And then, for example, all of the images that I've used, I figured out how many colors they actually take, and then noted where the start colors will be, or rather where the start of that color will be. So if I arrange all this for you in a nice, easy to see manner here, I'll explain these numbers. So these first numbers here, this is the starting location of that image's palette. So the ghost here, initially it had 256 colors, but then I converted the image by putting it into GIMP here. So I'll show you how I've done that, just in case you've not seen the 256 color tiles video. So I select that image, copy it, and then paste it in here as a new image. And then go into image at the top here, mode, indexed, and then make sure it's generate optimum palette, and then select what colors you want the image to be enabled with. So for my case, I allowed it to have 32 colors. So I'll show you now. If you drop that down and convert it, you'll see that's totally dropped that image. Now what you do is you'd copy that out back into LibreSprite and then save that, and then make a note of how many colors you've said that it's got, because once you use my image converter program, which I would recommend you use, I'm not really sure how you would do this with the image converter stuff that the DevKit Pro team provide. When you're working with 8-bit images, whether that's tiles or sprites or bitmaps, you need total control over the image and its colors. So if I open up my own graphics converter here, so as we are working with bitmaps, we need to select this one here for 256 color bitmap mode. And as we have not defined a palette in the top left of the image, we need to select this mode here so that it gets the image from the palette. Sorry, the other way around, it gets the palette from the image. So this is our image here, so now we need to locate it in the folder. Oh yeah, we need to set the size as well. As there's 3 of the images in here, they're 64 by 64, so you need to set the size of each tile in the image. And in the case of our ghost here, it's not going to be the start color is 104. So we put that as the start color for the ghost. And then we also select this option here to remove the first color and replace it with color 0. And then we can drag and drop it in like this. So this isn't the one we want to use. This is the 256 color one, so we won't be using that one. This is the one we want to use. There we go, found 33 colors. So what this will do here is it will remove that blue color and replace it with color 0 instead. Now if we only save this, it will say it's saving 3 tiles. So I've already saved this. As you can see here, what I've done is I've noted the start color and how many colors are in the graphics file there. And as you can see, it's saying 3 tiles. That's obviously 3. Each of these images will then be separated when it exports the data. So it will export this first one here, then the second one, then the first one. So they are clearly separated in the array. And then when you look in here, at the ghosts, you can open it in a text editor. You'll see here it's only exported 32 colors there. Start color is 104, which has got a few there, and it says there's 3 tiles in the image. And then what all of these numbers refer to here is these are all references to the color and the color palette. So these are all pixels here, and as you can see, it's replaced the blue color, which should be 104, with color 0. The reason for that is the blue color is obviously going to be a transparent color. We don't want that to be drawn. So by doing the remove color 0 option, that means we can not keep the blue color. So when it comes to larger images, so for example, all of those pictures, I set aside that I wanted a maximum. They could have a maximum of 96 colors in each of those images. So then what I did was I found some images online. So if I open up a few of them here for you to see. In fact, I'll just open one up a minute. So here's one of them there. This has been converted to 256 by 192 for the actual size of the screen. And then to convert that, I put the image through the GIMP program and added a div to it as well, and made sure that it couldn't have any more than 96 colors. And there's a number of different backgrounds which I'll show you in a demo shortly, and all of those have been limited to have a maximum of 96 colors. However, once you take them out of the GIMP program and then drop them in my image converter, one thing to note with the pictures is you don't want to remove color 0 from those, as there shouldn't be any transparent color in them, as they're going to be backgrounds. You only want to remove a transparent color if it's going to be like a sprite. Obviously these are like virtual sprites. I refer to them as like blitter objects, which is a name from early sort of DOS era and the Amiga era, where you had to kind of use a process of drawing like bits at a time from one image over to another image, which I'll get into shortly. So as you can see, make a note of the starting colours. And then one thing I did as well was although I'm not using the this duck character in the demo, if I open it up, you'll see here I've defined 2 pixels at the top here in it. This is because I'm having a bitmap font. No, sorry, I'm having a tiled layer for a font, so I can print text to the screen. The ducks palette will be configured first in the palettes. So the first 15 colors will be shared with the tile layer as well. So the font will be using these colors, and then all I did was I then deleted this top row of pixels from the image. So what I'll do now is I'll jump into the demo. So I'll show you that first. So what we've got here, this isn't obviously fitting on the full screen, is we have one image in the top, one image in the bottom. What I've also put in is I'm reading the touch screen at the bottom, so if you touch the screen, it'll paste a random star where you touch. And if you hold it down, then you'll get a different frame from the star. And then if you press left and right, you'll see the background bitmap drawing a different background image. And then up and down will cycle through the various images that I've converted and put in as well. Obviously it looks a bit grainy through the monitor here, but obviously when you put this on an actual DS screen, it will obviously look a lot better. And then if you press the A button, I think it's A. It's difficult to tell because I'm obviously using the keyboard here. I'm using the emulator, not the actual DS, to show this. So it will draw a random ghost, one of the frames. So what I've also created here is I've created like a virtual screen in memory. The reason why you would do that is because you can then write bytes to it and read bytes from it, which you can't do when the image is obviously in video RAM itself. You can only work in words, or rather unsigned 16-bit numbers. So by creating a virtual screen in memory, we can do all sorts of manipulation to that, and then copy half of it to the top bitmap layer, which is the middle layer on the top here, and then the same for the middle on the bottom layer. And then if we press the other button, we will get a large prime image being drawn, and then the left and right buttons will clear the middle sort of bitmap layer. So that's pretty much the demo, which I would encourage you to have a play around with. And I'll jump into the code and show you some of the key bits in here. So the main thing to note here is we are using mode 5, which gives us the ability to have 2 bitmap screens. So I've set them to be enabled here. We're using background 0 for our tiled screen. And then we are using background 3, which is the bottommost screen. So background 3 for the main and the sub screen. That's where we are drawing the full screen images to. And then the bitmap at background 2 is being used as our kind of drawing surface, if you like, where we can draw parts of images as we please. So the best bit about using the bitmap screens is obviously you can you don't have to worry about tiles. So you can, if you've got methods to draw part of an image at any place on your bitmap, then you can obviously create virtual scrolling. You can scroll level tiles onto and off of the screen as you please, just by drawing them at certain locations, as long as you have functions to clip parts of the image when it goes outside the boundary of the screen. I'll quickly open up Inkscape again here and go over some of this, as this is some stuff that you will need to get your head around if you've not worked with bitmaps and blitting before. So say we have our screen here. So this is our screen here, and then we have a number of different images. So let's draw a star there. Now, everything is essentially inside of a rectangle here. So I'll just configure the size a minute. Just line that in there and then group that. So everything you can think of as being like a rectangle here, and then the screen is being treated as a bitmap, and this essentially is also a bitmap, with the top left pixel being at 0, 0 in this other smaller bitmap. Now if you draw it so that it's fully inside here, then that's a simple process. You're literally just copying the top left from here into the starting location inside the screen here. However, things get a bit complicated if it's slightly outside here. So you have a part of this here that, so if I highlight this here and then change the opacity here, fact, that's not a good colour. Let's change that there. So the part of this image here that we would actually need to draw would be this subsection here, which is overlapping with the screen. So you have to calculate how many pixels on the left side to skip to get to the part you want to draw, and also how many pixels at the top here you would need to skip to draw. As there is no clipping, which is what this process is called when you draw things normally, where certain parts of the image which are outside the boundaries of the screen are not drawn. What you actually have to do there is you have to get the offset at the top and the offset from the left inside the array of this image here to start drawing. I have functions which handle all of that. So every time that an image is partly outside the screen, you need to work out only the intersecting part. Otherwise, you will cause memory corruptions, because you would be writing parts of the image which don't need to be drawn. So this would also cause various distortions in the image as well if you don't calculate it correctly. So that was just something that I thought might potentially be of use to you if you've not encountered working with pixels directly before when it comes to drawing images. So all of the images are obviously in arrays. We have an array for their palette, an array for their pixel. And then the key thing with all of this is recording exactly what they all use. So we have a font layer, which if we come to the S2D initialization function here, when it comes to wait, I'll come down here. So we have our font layer, which is background 0, and you'll see we've set the tile set to 0 and the tile map to 1. I'm assuming you will have seen the tiled videos. If not, you'll need to check those out to understand what's going on there, as I'm not going into it here. So what we've set up here is we have some color start defines. So all of those pictures, I gave a limit of 96 colors. These are the amount of colors they actually have. When you actually convert those images in the image to DS converter, because of the actual red, green and blue values in those images, they can't be converted into proper 16-bit numbers due to the limited range within 16-bit color palettes. So lots of the colors end up merging together, hence the reduction in numbers when you convert them. But you need to know how many colors each of those images take. So when you swap out one image for another, not only do you have to draw that image, but you have to load in to palette RAM the new colors. That's why you need to note how many colors is the maximum range, so you can easily replace things by swapping them out for replacements. If you think of like 10 different levels in a game, each level would probably have its own unique colours and graphics. So to be able to interchange parts between different levels, you need to know where the colours start for those parts and what the maximum range of allowable colours are for each part. So here CC stands for colour count, CS stands for colour start. So this is just organising the colours so we can easily work with the images. And then we are just working out the sizes of these images here as well. So we have some enumerations here so we can easily work with everything. And then most of the core stuff for the setup is in S2D or Scene 2D, as I refer to it myself. So we've got some defines here. We work out how many bytes one of the screens will take. This is so that we can literally fast copy one of the background images to the actual video RAM location of the layer which will be displaying that image. So this is how I've arranged them here for the array which will hold the background structures here. So when it comes to setting up the bitmap displays, you'll see we use the tile map attribute, the pointer for the tile map. And that's because the tile map attribute has a range of 32 attached to it, which allows us to get to the very sort of bottom of video RAM for the main and the sub engines. So if I uncomment the background header file there, then this will allow me to show you the various sizes in autocomplete. So you'll see here everything with BG size B8 next to it is the available size, and then the info code here points out how many bytes each of those no, sorry, that isn't the case. It's just a number which it stores in there, I guess, to set that up. So when working with 8-bit bitmaps, all of the sizes would have a BG size B8. And then the only number we're interested in here is the map base number here. But when it comes to the bitmap screens, this is in steps of 16K. So you'll kind of need to try and visualize where everything is fitting together. And then what I also have here as well is I have two pointers which I've set up for the source surface destination top and the pointer to the destination surface top. This is for quickly drawing stuff. So you'll see here this array here. This allows us to treat one large surface as one virtual sort of screen. So this surface actually covers both of the background layers. So there are a few. There's one drawing command which I'll put in, which is just the pixel set command. So you could use this to plot pixels anywhere on the screens there. And then there's a few error catching things in here as well. This is just setting up the various screens for us here. One thing to note here on the sub screen is there wouldn't actually be enough memory to have 2 bitmaps and a tiled layer. So what's actually happening here is bitmap 2 and bitmap 3 are overlapping slightly so that everything fits into one 128K memory bank. As I said in the slides, a 256 by 256 screen obviously has 16K, which isn't being used. So what I've actually done is background 3 overlaps the bottom part of background 2, but as background 2 isn't using that extra 16K of video RAM at the bottom, it's not missed at all. So you can squash things together if you're careful. So I won't go over any of the printing commands here for text or the tile-based stuff, as in the tiled commands here, as they're the same from the tiled videos. The key ones I'm going to go over here are some of the blitting functions here, which is the process of transferring bytes from one image to another. First off, I'll go over the blit backgrounds. All this is doing here is this is drawing the faux image screens, so that the backgrounds, if you like. So as I'm here, I'll explain the clear, everything with a surface in there refers to the bitmaps. So we have a clear surface both command, which will convert the pointer to video RAM into an unsigned 32-bit pointer. The reason why I'm doing this is it means we are actually able to write 4 pixels at one time, as there are 4 bytes in an unsigned 32-bit number. And then we just go over the loop and write 0 at the location in video RAM in steps of 4 bytes, if you like. As we can't write bytes directly, we have to use either U32 pointers or U16 pointers. But obviously if we can use U32 pointers, then that will obviously be 4 times as fast as writing just 1 byte at a time, and twice as fast as writing a U16 at a time. So I decided to have also a clear bottom and a clear top. As in the demo, you can see we can use the touchpad to plot characters on the bottom screen. So you might want to clear the bottom screen only. Again, you could avoid using a tiled font altogether and then just totally go through like a small bitmap font of any size you please. But the obviously the more drawing of bitmaps that you have, the more performance loss you're going to get. Although it might be marginal depending on what you're doing. And then we are using the DMA copy command to literally draw the bottom surface and the top surface. So these draw bottom surface, top surface and full screen, all these are doing here is this is literally just transferring parts of the surface here to the corresponding video RAM for the background layer. So background layer, where is it? Which one is it? Yeah, here we go. So background layer 2 is the where the top destination surface pointer points to. See this command here, this is what we need to get the video RAM pointer for the bitmap. And then we are then copying that pointer into the destination top surface so that we can draw the top part of our virtual image in here to video RAM. And then we are doing the same with the subscreen here. So this part here sets up the relevant background for the subscreen. And then we set the destination bottom pointer here, so that when we once we're finished drawing all of our virtual sprites and images to our virtual screen, we then need to synchronize that to the video RAM, as in we need to copy that across, which is what each of these commands do here. So they allow you to draw part of the screen independently from the other part, or if you want to update them both in one go, then draw screen full will do that. And then in the pix set command, we're literally just writing the color directly to the surface array here. Bear in mind there's no check-in where you're writing on the screen here, so be careful. And then these commands here, the blit backdrop image, these are the commands responsible for drawing those background images directly into video RAM. So first off, what we do is we take the colors for those images and then load that into the main palette here, as this is the top screen. We then create a U32 pointer from the pixel array passed in. We then create a U32 pointer from the bottom background layers memory pointer, and then we literally just use a for loop to quickly write U32s between them to allow us to quickly draw an image. So there's no synchronization needed here. This is literally doing it all in real time, but as it's happening so fast, you don't notice those things being written. And then there's two functions for drawing mini bitmaps into the larger screen. This one here, blit image, which is not demonstrated in this demo here. This would be used for images which do not have any transparent parts. So for example, like background tiles, like floor, walls, obstacles, that sort of thing. As long as they have no transparent parts. The reason why you'd keep this separately is because when it comes to drawing images with transparent parts, they are slower to draw because you need to compare each pixel to see whether it matches the transparent colour. If it does, then you don't plot it to the bitmap. If it's not transparent, then you obviously draw it, but having to compare that each time slows things down. So all we are kind of doing in the pixel blitting routines is, first off, we need to make sure that the our image we wish to draw, its surface overlaps the relevant screen surface we are drawing against. If it doesn't, then there's no point going any further, as there's nothing to draw. And if you do try and draw, then you'll be writing pixels to somewhere random in the memory of the DS, which could potentially cause the machine to crash or give you various graphical glitches. And then the next bit we do is I've added another routine, another function here called rect inside, as what we are checking here is to see that the our image we are drawing fits nicely inside the screen which we're drawing on. If it does, then we can do a really simple drawing loop, just like this here, where we literally just navigate over the whole sort of bytes in a simple fashion to draw that image. Things get more complicated if that isn't the case, as we need to work out which parts of the image is outside of that of the surface we're drawing onto. And then we also have to work out, first off, where we start taking bytes from in our pixel array, and then how many to skip. So all of the code is here for you to do that. Definitely have a look at it to get your head around what's going on. Sometimes you can, if you use Inkscape at all, that can be a great help to visually see what's actually occurring when parts of the bitmap are not being drawn. So essentially, when we come to draw it, we need to work out, as I was showing before, the inside starting location. and also the width might change as well. If the right hand side of the image we're drawing goes outside of the screen on the right hand side, then obviously we don't have to draw the full width, but we do need to know how many pixels to skip over, as the image is obviously in an array. And as we are going over an array normally 1 byte at a time, once we draw that partial width, we then have a number of pixels we need to skip over to get to the correct part we then need to draw again. So you see we draw the width and then we add number of pixels to skip for the destination. So the destination is obviously the actual DS screen or our virtual screen we're drawing onto, either of the two. So to work out the destination skip, that would usually just be 256, which is the width of the DS screen, minus the size of the image we are actually drawing. If you're not sure what's going on there, you might need to have a play around, maybe some read up on some DOS blitting routines. So these names here, transblit and blit, these are actually Win32 function names. So you could probably type in something similar and it might give you some more information on those. So the transblit thing kind of does exactly the same as the blit part, except in the case here we are skipping transparent pixels. So in the case of this demo here, I'm treating color 0 in our palettes as being the transparent color. So anytime you use transblit and it finds color 0, it will not draw it to the screen. It will skip over it. As when drawing sprites, or virtual sprites in this case, we would obviously not want to see the transparent parts being drawn. This just does exactly the same as the blit routine here. All it sort of in the extra bit it includes is, instead of getting our source pixel here and then putting it directly into the destination pointer, we first use a temporary variable to hold that byte. And then we compare that to 0. And if it's greater, then we'll write it. Otherwise, nothing to see here, you know. So that's pretty much the main details here. These are just everything's just in the main sort of title screen part here, the code. I didn't use this in the end. I decided to maybe I'll demonstrate a more complex scene when it comes to 16-bit bitmaps, which I will go over in the next video. So this obviously will be like a base for you to build off of. I would also say you can, if you search for some DOS-C routines, you might find some commands for drawing lines. Drawing rectangles is fairly straightforward. You can find drawing circle routines as well, which is a bit more complicated, but the code is out there. I decided not to bung any of it into this video. Maybe I'll put it into the 16-bit bitmap video. If anyone's interested, then leave some comments to say so. If not, then I won't. The idea is was just to sort of touch on this and then give you a demonstration of drawing bitmaps, and also to use touchscreen as well. So another thing I've added in here as well in the input manager side of things is recording touchdown events for the bottom screen, which is fairly straightforward. This touch read command here gets the details, and then we just record from this this touch position structure here. So if you uncomment that and then look in there, this has some functions in here. And then you'll notice that it refers to this structure here, which contains a load of other sort of details here. The only ones I was really interested in was the actual pixel X and Y positions. Not sure what these other variables refer to. I haven't sort of played around with that. This is the first time I've really sort of played around with using the touchscreen. Not very responsive, so probably won't do any more with that. But it's all in there for you to have a look at anyway. Hopefully this has been some use to you. Let me know if you've found this of use, or if you want me to go over adding some drawing commands in the 16-bit video, which I will do next. Right, I think that's it for this video. I will catch you later.